Okay, we're going to look at differentiation from first principles. We're going to look at the curve y is equal to x squared. First of all, we're going to put the first point on, and we're going to call it p, and it's going to have x as its x value, so its y value then would be x squared. Our other point then, we're going to call it q, and its x value is x, and I'm going to say x plus h, and its y value would be x plus h all squared. So as h gets smaller and smaller, which is what we're going to do for differentiation, we want to find what the gradient is at p. So as h gets smaller and smaller, what happens is this q will move further and further and further along, closer and closer to the p. So effectively, the gradient of this tangent here I've just drawn, it will get closer and closer. So you can imagine if my q is moved to here, my PQ is going to get a lot closer to my gradient of P. At here, it's going to get a lot closer. And if P was right here, right on it, its gradient is basically, the gradient of P to Q is basically going to be the same as the gradient of the curve at the point P. So that's really what we want to do. Okay, so let's just look at the gradient of PQ. So the gradient of PQ would be equal to, and this is just your y difference over your x difference, it's just going to be x plus h squared, that's my y value of q, minus the x squared, which is my y value of p, over the x plus h, which is my y value of q, minus my x value of p, q, minus my x value of p. Okay, that's a bit of a mess, we're just going to tidy it up. Multiply at the top line, you're going to have x squared plus 2h x plus h squared minus x squared, and your bottom line, you've got x plus h minus x, which is just h. Again, we can tidy up your top line, which just gives you 2hx plus h squared all divided by h. Then what we can do is divide through by our h and see what we get. So dividing through, what we're going to get is 2x plus h. So that's what we get. We get 2x plus h. Now, what we're actually going to be doing, remember what we were talking about? We were going to move our q, the point q. So what we're doing is we're making h the difference between the x value of p and the x value of q. We're making the h very small. So basically q is moving closer and closer to the p. So basically what we want to do is make the h, the difference between these two things, infinitely small. So if we just look then at what we had, we will just say that our gradient of the tangent at P is when h tends to 0. So if h tends to 0, you're going to have 2x plus 0, so it is just equal to 2x. So really what we can do is we can say our dy by dx, that's your derivative of y with respect to x, is 2x. In this example, we're just going to do another line which you already know the gradient of, y equals 3x plus 2. So we already know the gradient of this line is going to be 3, but we're going to prove it really using our first principles of differentiation again. So if you've got a point P, which is x, and then 3x plus 2, and your point Q, its x value is x plus h, its y value then is 3 times x plus h plus 2. So the gradient of PQ will be equal to 3x plus h plus 2 minus 3x plus 2 all over x plus h minus x. That's just your y difference on the top and your x difference on the bottom line. So if you were to do that, out and tidy that up, what you will get, multiply the top line and tidy up, you'll just take a couple of lines to that. 3x plus 3h plus 2 minus 3x minus 2, and your bottom line, what's it going to be? It's just going to be x plus h minus x. Let's write that out, x plus h minus x, and again tidy that up and see what we get. Top line, you've got 3x minus 3x, they cancel, then you've got 3h, and then you've got 2 minus 2, which is 0, and the bottom line, you've just got h. Now if you look at this, if you look at this, what happens? It clearly just, the h's cancel and it gives you 3. So in actual fact here, it doesn't matter if you just look at just this diagram here, you can see the gradient, we have shown that the gradient of PQ is 3. So if you move Q closer and closer to P, so it's right on top, the gradient at P is also going to be equal to 3, or if you moved your Q further away in this case. But really what our differentiation is trying to show is just say, therefore, your dy by dx is equal to 3, and again, that is at the point of P. Now you could extend this and you could look at other functions. You could look at y is equal to x cubed, or anything else at all. You could look at y is equal to 2x squared plus x, and you could show the same thing by differentiation by first principles. It wouldn't be easy, but you could do it.